A downed Black Hawk does not look the way most people imagine. It is rarely a clean wreck sitting upright in an open field, waiting to be lifted. More often, it rests at an awkward angle, half buried in soft ground, tangled in vegetation, or split across terrain that no truck can reach. The rotors are bent, the tail boom is folded, fuel may still be in the tanks, and the question facing the recovery team is not a simple one. Can this aircraft be moved without destroying what remains of it? Because the wrong decision in the first hour can turn a recoverable airframe into scrap. Recovering one of these aircraft is one of the most complex jobs in modern aviation logistics. It is part engineering, part salvage, part security operation, and almost none of it looks the way a short video clip might suggest. To understand what the work really involves, you have to start with the machine itself. The UH-60 Black Hawk has been the backbone of American military rotary aviation since the late 1970s. It replaced the Vietnam-era Huey and was designed from the beginning around survivability. Twin General Electric T-700 engines, a fully articulated four-blade main rotor, crash-worthy fuel cells, energy-absorbing landing gear, seats that compress under vertical impact to protect the spine. Even the airframe itself is engineered to deform in a controlled way during a hard landing. It absorbs energy instead of transferring it directly into the crew. That survivability is exactly why so many Black Hawks end up needing recovery rather than write-off. The aircraft is built to keep flying through damage that would ground other helicopters. It is built to land hard without killing everyone inside. So when one goes down, there is often something left to recover, sometimes a great deal. The same engineering that protects the crew also makes the airframe difficult to move once it is on the ground. A Black Hawk is a heavy machine. Its weight varies significantly depending on configuration, fuel state, and mission load. After a hard landing, that weight does not go away. It just sits there, often distributed unevenly across a deformed structure, with components that may or may not still be load-bearing. The recovery team cannot simply hook a cable to the strongest looking point and lift. If they pick the wrong attachment, the airframe twists, the skin tears, and the aircraft becomes far harder to save than it was an hour earlier. This is where real military helicopter salvage begins, long before anyone touches the wreck. It begins with a decision. The first question is not how to move the aircraft. The first question is whether to move it at all. Every downed airframe falls into one of a few categories. It may be flyable after field repair. It may be recoverable but not flyable. It may be recoverable only in pieces, or it may be a total loss, where the priority shifts away from saving the airframe and towards securing what is on board. That last category is the one most people never think about, but it shapes the entire recovery plan from the first minute. A Black Hawk carries communications gear, navigation systems, identification systems, and in some configurations, mission-specific electronics. The military has strong reasons to make sure none of that equipment is left behind, recovered by the wrong people, or studied by anyone outside the program. Before any lift, before any rigging, before any heavy equipment arrives, those components have to be accounted for. The exact procedures vary with the situation, the location, and the threat. What stays consistent is the principle. Sensitive equipment is the first priority. The airframe is the second. Only after that priority is settled does the engineering side of the recovery really begin. The team responsible for this work in the U.S. Army is built around aviation maintenance units, with specialized downed aircraft recovery teams trained specifically for this kind of operation. They are not improvising. They are working from established procedures refined over decades, and they bring tools designed for the job. Slings rated for the airframe, rigging points mapped to the aircraft's structural drawings, lifting bridles engineered to distribute load across the strongest parts of the fuselage. Nothing about this is generic. When the team arrives at the site, the first real task is assessment. They walk the wreck. They look at how it sits. They check the angle of the rotor head, the condition of the tail boom, the position of the landing gear, the integrity of the cabin floor. They look for fuel leaks, hydraulic leaks, and any sign of fire damage that might have weakened the aluminum structure beyond what the eye can see. Aluminum is forgiving in some ways and unforgiving in others. It bends before it breaks, which is good for crash survival. But once it has been heated by fire, its strength can drop dramatically without any obvious visual change. A spar that looks fine can fail under load. That is the kind of detail an inspector is trained to find before anything heavy is attached to the airframe. The rotors get special attention. A Black Hawk's main rotor blades are made of composite materials with titanium spars and leading edges. They are tough, but after a hard landing, they are almost always damaged, bent, cracked, or sheared off entirely. The rotor head itself, the hub that holds everything together, is one of the most stressed components on the aircraft. If the blade struck the ground or struck the tail boom during the crash sequence, the forces transmitted into the hub can be enormous. Even if the hub looks intact, it may be internally compromised. In most recoveries, the blades come off before the airframe moves. They are unbolted, secured, and transported separately. This reduces weight, it reduces wind load during a sling lift, and it prevents further damage to components that may still be salvageable for inspection or parts reclamation. The tail boom is the next consideration. On a Black Hawk, the tail boom is a long, relatively slender structure. It carries the tail rotor drive shaft, the intermediate gearbox, the tail rotor gearbox, and the tail rotor itself. In many crashes, the tail boom is the first thing to fail. It may be folded, twisted, or completely separated from the fuselage. If it is still attached but compromised, the recovery team often removes it before lifting the main fuselage. The Black Hawk was actually designed with this in mind. The tail boom can be folded for shipboard storage, and the same design logic helps during recovery. Once the aircraft has been stripped down to a manageable core, the question becomes how to get it out. And this is where the environment takes over the conversation. A Black Hawk that goes down on a paved airfield is one problem. A Black Hawk that goes down in a rice paddy, a mountain ridge, a desert wadi, or a forest canopy is an entirely different problem. The recovery method has to match the terrain, the threat level, the weather, and the time window available. The fastest recovery method, when conditions allow, is a sling-load by another helicopter. The CH-47 Chinook is the workhorse for this in US service. With its tandem rotors and heavy lift capacity, the Chinook can pick up a stripped Black Hawk and fly it to a secure location, depending on configuration and conditions. The procedure is precise. Riggers attach a multi-leg sling to engineered hardpoints on the Black Hawk's airframe. The Chinook hovers overhead. A ground crew member, often called a hookup man, connects the sling to the Chinook's cargo hook. The Chinook lifts, stabilizes, and flies away. From the outside, it looks almost simple. From the inside, every variable matters. Wind, density, altitude, the weight of the load, the swing characteristics of the slung aircraft, the distance to safe ground. A slung helicopter is not aerodynamically stable. It wants to spin. It wants to swing. The pilots managing that lift are flying two aircraft at once, and one of them is dangling on a cable beneath them. When a sling load is not possible, the recovery becomes a ground operation. The aircraft has to be disassembled further, loaded onto a trailer or a heavy equipment transporter, and driven out. This sounds straightforward until you consider that the aircraft may be a long way from the nearest road, on terrain that no trailer can cross. In those cases, the team may have to build a path, cut vegetation, lay matting, bring in a crane, or break the aircraft down into smaller sections that can be carried out by smaller vehicles, or even by hand. In maritime recoveries, the problem changes again. A Black Hawk that goes into the water is fighting corrosion from the moment it enters. Salt water attacks the aluminum airframe, the magnesium gearboxes, the steel fasteners, and the electrical systems all at once. Every hour underwater reduces the chance of meaningful restoration. Recovery teams working over water typically use barges, divers, and lifting equipment rated for marine conditions. The aircraft is often raised in stages, stabilized at the surface, drained of water and fuel, and then transferred to a recovery vessel for transport to a depot. Even with fast action, an aircraft that has been submerged for an extended period is rarely returned to flight. It becomes a source of components, a training airframe, or a write-off. This is the part of recovery that the dramatic versions of these stories tend to skip. Not every downed aircraft is saved. Not every saved aircraft flies again. The military uses a tiered system to decide what happens after recovery. The aircraft is inspected at a depot, where engineers and technicians strip it down and evaluate every major component. The airframe is checked for hidden damage. The dynamic components, meaning the rotors, gearboxes, and drive shafts, are inspected with non-destructive testing methods. The engines are sent to their own overhaul facilities. The avionics are tested or replaced.
By applying fluorescent particles and utilizing UVA light, we can clearly identify discontinuities in the material surface.
If the airframe is structurally sound and the damage is repairable within cost limits, the aircraft can be rebuilt. Black Hawks have been returned to service after damage that would have written off a civilian helicopter. The military has a financial and operational incentive to save what can be saved, because a rebuilt airframe is faster and cheaper to put back in the fleet than a new one. But there is always a threshold. If the cost of repair approaches the cost of a new aircraft, or if the structural damage is too distributed to fix with confidence, the airframe is condemned. Its serviceable parts are removed and returned to the supply system. The hulk itself may be used for training, for battle damage assessment studies, or scrapped. This is what saved actually means in military aviation. It does not mean a miracle restoration. It means the aircraft was recovered intact enough to be evaluated, and that evaluation produced the best possible outcome given what was left. Sometimes that is a flying aircraft again. Sometimes it is a parts donor that keeps other Black Hawks in the air for years. Both outcomes are wins. Neither is the kind of story that fits into a 30-second clip.
A slow parallax move along the seam reveals the subtle difference in paint sheen between the restored and original surfaces, yet the geometry remains stable.
There is another dimension to this work that deserves attention. the human one. Recovery teams are working in conditions that range from uncomfortable to genuinely dangerous. They may be in a remote area with limited support. They may be working in extreme heat, extreme cold, or at night. They are handling a damaged aircraft that may have residual fuel, pressurized hydraulic lines, and sharp deformed metal everywhere. The work is physical, technical, and slow. A typical recovery operation can take anywhere from a few hours to several days, and the team is often planning the next steps while the current ones are still in progress. There is also the emotional weight that comes with some of these operations. Not every recovery is routine. Some aircraft go down with crews still on board. Recovery in those cases is handled with a different kind of care, and the people doing the work understand exactly what the airframe represents. That is part of why the procedures are so disciplined, and part of why the teams who do this work tend to talk about it in measured, careful language. They are not chasing spectacle. They are doing a job that matters. Step back from the individual recovery, and a larger pattern becomes visible. Every Black Hawk that is brought home, whether it flies again or not, contributes to the long-term sustainment of a large fleet. The U.S. military operates the Black Hawk across multiple services, with Allied operators flying it as well. The aircraft has been in continuous production since the late 1970s, with successive variants improving the engines, the avionics, the rotor system, and the airframe. Keeping that fleet flying depends on a supply chain that includes new parts, overhauled parts, and parts reclaimed from recovered airframes. Recovery is not a side activity. It is part of how the fleet stays in the air. Recovery is also part of how engineering knowledge accumulates. Every recovered airframe tells a story about how the aircraft behaved in a real event. Engineers study the deformation patterns. They look at which components failed and which held. They feed that information back into design improvements, maintenance intervals, and crew training. The Black Hawk that flies today is a more refined machine than the one that entered service in the late 1970s. Part of that refinement comes from the lessons learned in recoveries that the public never hears about. What looks from the outside like a single dramatic event is really the visible part of a much longer process. It begins with design decisions made decades ago. It runs through the discipline of the recovery team. It continues at the depot, where the airframe is evaluated, and it ends in a hangar, or a parts bin, or a scrapyard, depending on what the aircraft can still give. Every step is governed by engineering judgment, not by hope. That is the real story of recovering a Black Hawk. It is not a rescue in the cinematic sense. It is a careful, deliberate process built on the assumption that the aircraft is worth the effort to evaluate, and that the people who flew it deserve a system capable of bringing it home. The lift, when it happens, is the easy part to photograph. The decisions that make the lift possible, the assessments that determine what survives, the depot work that follows. Those are the parts that actually define the operation. A Black Hawk on the ground in the wrong place is a problem with many possible answers. Recovery is not about finding the most dramatic one. It is about finding the right one, in the time available, with the people and equipment on hand, and with respect for what the machine was built to do. When the work is done well, the aircraft either flies again or gives its remaining life to keep others flying. Either way, it is not abandoned. And that, more than any single lift or any single image, is what military helicopter salvage really means.